All right, yeah. I can only join courses in saying thank you everyone for being here, and yeah, happy to see really the Flink community come together on days like this, and so many new faces being interested in this project. I want to talk a little bit about, Kostas already hinted at it, at some of the technological developments that we're doing, and I'm going to take a little more of a, let's say, conceptual, theoretical view at things, and Xiaowei is going to follow up and give you a bit of the details of what we're actually doing in practice. So first of all, if we look at all the use cases from the, I've made an effort over the last months, like continuously trying to look at the different efforts or the different use cases that companies are implementing on Apache Flink, and trying to see, how are they actually using the system, using the APIs, what kind of use cases are they doing? There's a few interesting ones coming up. It's kind of a new development this year, I think, that Flink is somehow making a good way into the public cloud. So it's being actually used both in Alibaba Cloud, in Huawei Cloud, and in Amazon Kinesis Data Analytics as the stream processing system, as the analytical system. And there's also kind of a really nice relationship with the Apache Beam project that gives a really interesting hybrid cloud story with Google Cloud. People develop their applications in Beam, can run it on a managed service in the cloud, can run it on Apache Flink on premises. So what is the spectrum of applications that we see people developing, and how did that actually influence us in further developing Flink, and how did this bring us to the initiatives we're doing at the moment in the open source community? To me, looking at the stream processing space, it's always been a very big spectrum. Stream processing is not just a technology to do some real-time statistics, real-time aggregates, real-time event processing, but it's always been like a very big spectrum covering use cases from a lot of processing historic data, when we call this lag time processing, to processing hard real-time data. So kind of spanning the entire spectrum from batch processing over continuous processing, real-time data pipelines, streaming analytics, event-driven applications, and even almost OLTP-style transactional processing. And all of these use cases in stream processing, in my mind, they always kind of navigate the spectrum in somehow two dimensions, I believe. They're a little more, some are a little more continuous streaming, some are a little more like continuous processing, going towards the direction of batch processing or periodic batch processing. And some of them are more like, clearly analytical applications, and others are really like more application-y applications, like business logic, event-driven business logic. So over the last years, I would say the Apache Flink community is focused probably mostly in those use cases, their efforts, right? So it started out as a system. I would say the first use cases that Flink was adopted for were probably more in the area of continuous processing, data pipeline, streaming analytics. I think event-driven applications has kind of come up over maybe the last 1 or 2 years as an interesting use case as well. And if you look at where the majority of the effort of the Flink community went, I would say it's those use cases here, right? So in some sense, Flink has tried to cover a good amount of use cases in the spectrum, but there's something left to the right and left here. Just some examples. If you actually look at the latest released version, which is 1.7, 1.8 is probably coming out any day now. Some of these features were time version joins, match recognize, schema upgrades for stateful processing. These are all features that kind of make people's life in those use cases easier. We have actually, as a company, made an effort to tap into these kind of use cases. So the last keynotes at Flink Forward Berlin and Flink Forward China kind of introduced some new technology that we built for actually doing transactional processing, like think of it as multi-partitioned, multi-row serializable transactions by way of stream processing. So if you're interested in that, I'm not going to talk about that in this keynote. There's a talk, I think in the next time slot. What I would like to focus on here is exactly the other side of the spectrum, batch processing, right? In this diagram, it sounds like just like this one bubble, this one circle, but it's in fact actually a huge space, and probably, yeah, it's a much, I would say, much older space actually even than real-time stream processing. There are a lot of developments that are currently happening in the Flink community to branch out in that direction. So around batch performance and fault tolerance, machine learning, graph processing, SQL ecosystem, and batch processing related tooling like interactive queries and dashboard integrations. What I would like to do now is take a moment and look a little bit at how do we actually think about batch processing in Apache Flink, right? Because I want to really stress that we're not saying, okay, we've actually built stream processing technology. Now we're just starting a completely separate effort, and we're trying to do something else, like we're building a second Flink stack next to the actual stack, right? That's not how we're thinking about it. We really think about batch processing as a special case of stream processing, and what does that actually really mean? Like, what is the relationship between batch processing and stream processing? How do we think about it in the community and in this project? So, yeah, the relationship between the two. I kind of said it before in one sentence, batch is a special case of streaming. I think this phrase has been floating around for a bit. So, people say this, batch is a special case of streaming. What does that actually mean in detail? Does it just mean, as soon as you can do streaming, you can do batch processing as well? Kind of yes and no, I think is the answer. And so in a very simple way of looking at it, this is obviously true, right? If you do stream processing as processing unbounded data streams, then you can obviously process bounded data streams. So far, so simple, right? So if we look at, this is one of the graphics we like to use in Flink. Think of, data as a stream started somewhere in the past, going into the future. You can do stream processing as in just attaching to the data stream now, continuously processing into the future, going back to the beginning, starting there, crunching through all the data in the past, kind of falling in with the real-time data rate, continuing to process in the future. Or you just take a slice of data from the past, and then you have a classical batch-style use case, just a static slice of data from the past. So in that sense, yes, batch processing is a special case of stream processing, but I think this is about 60% of the truth only, because you can think about it like if you've used Flink for a little bit, you can kind of see this in a very obvious case, right? You can use the DataStream API, for example, to process a bounded data stream, but it's probably not the best idea to actually do that if you're processing data from the past. It's probably better to use the dataset API, which is much more efficient at doing this. And why is that actually the case? Like, if all that batch processing is a bounded stream, then why is data stream and a bounded stream? Why is that slower than dataset? And why is not every stream processor like just killing all the batch processors out there? So the remaining 40% of the truth is actually, I think, in these aspects, right? If you do continuous stream processing, like all the continuous streaming systems are kind of built around the assumption that if you're dealing with data that's coming in real time, you're dealing typically with data that's inherently incomplete, right? Events come in. You have a certain amount of time to produce some amount of answer. That is usually some form of latency SLA, and all the processing you do is kind of treating off the latency and the completeness, right? If you wait a little longer, you might see a few more events and produce a slightly more complete result. But then, the latency is higher, so you're eventually trading this off. Versus in a batch job, you're just starting this, and this is the data that goes into the job, and this is all it is. And you usually don't have like a millisecond SLAs to produce your first data point when you start a batch job. And like very, very practically, where does that manifest for example, for Flink users? I think this manifests most obviously in the fact that stream processing uses watermarks and batch processing doesn't. Because watermarks are exactly that. Watermarks are the trade-off between latency and completeness. This is how you define your watermark generation. How much do you want to like make the watermark lag behind to just take a little more data versus, keep your latency under control. So in some sense, you could think doing stream processing and like not generating watermarks, but just holding the watermark back to the end forever and doing it all, doing everything at the very end. Like just accumulating all your data in the windows and emitting everything at the very end. Latency, completeness trade-off-wise, that would actually get you close to batch processing. That is actually right. So why are we not, for example, doing this in the DataStream API? Now let's look a little bit at what's happening underneath the hood. And I picked one operation that's kind of both common and complex, I think, in like data processing here, which is the streaming join. So this is a comparison between how a continuous real-time join works compared to how a batch join works in Apache Flink. And you can see the vastly different data structures and algorithms at play. The continuous streaming join uses basically 2 RocksDB LSM trees, RocksDB column families here, versus 1 hybrid hash join table on the batch side. And why do we actually use different algorithms here, right? Because they actually exhibit vastly different characteristics. The way that the continuous streaming join works, it works with push-based operators, which give you low latency, which have the effect of minimizing in-flight data, which is really good if you want to do like distributed checkpoints like Flink does. Versus on the batch side, pull-based operators, flexible control over the data models, that's what you need to support algorithms like hybrid hash join. But it leads to higher latency, and it's not very trivial to do checkpoints like that. And this is in some sense what happens, for example, underneath the DataStream API and the dataset API. The batch hash join being a like vastly more efficient algorithm to do this, versus the streaming variant is the more general algorithm, right? You can use it to produce incremental, intermediate, low latency results. You could also use it, you can also produce batch results that way. It's just more expensive. So how are we trying to rethink the runtime when we approach batch processing? So you can think of it as the following case, as the following way. So yes, batch is a special case of streaming, but you also really need to exploit that special case. Otherwise, you're not doing it very well. So the idea how we're like rethinking the Flink runtime at the moment is think of a data stream program going through some form of like planner optimizer. It can be a like more sophisticated planner optimizer in the case of a SQL table API, or a very straightforward transformation in the case of the DataStream API. And it goes to typically a set of continuous operators, streaming scheduler rules. This is the core. This covers all cases, the batch and the streaming case. But for the algorithm where it's relevant, it's not relevant for all, but for some, for example, like the join algorithms, you can think of it that there's some rules in the optimizer that look at the program and say like, hey, some optimizer rewrite rules, like in SQL. If this is a bounded program and you're not interested in incremental aggregates because we're not dealing with, like with watermark triggers or event time, processing time triggers, then we just have a few additional optimizer rules that select a few additional choices. It will actually activate the hybrid hash join operators. And in most cases, these are like by pure cost trade-offs, just going to replace the streaming variants of the operators. Now, that might actually not even always be the case. There's actually arguably even the cases that if you're processing something that really, you read it as a stream, it's kind of already in sorted order by time and so on, you might actually still use the streaming variants even though you're in a batch case, but that's probably rare. So this is like a nice way to think about it. Batch is really a special case of streaming. It's just a few additional choices that, let's say, a planner and optimizer has when it knows that it's dealing with bounded input and it doesn't have these like incremental result SLAs. So maybe just a few words on the other dimension that we were looking at applications versus analytics here. You might have seen this figure before. It might be either on the Flink website, or at least it's in a whole lot of Flink presentations that we gave in the past. And we kind of showed, this is the API stack. On the lowest level, event, state, and time. And in the middle is the DataStream API, and then on top of it, you go for, you go a bit more high level with streaming SQL and the table API. What we really found over the recent years is that that a lot of users are, based on what they're doing, gravitating into one of these two APIs based on the following characteristics. Let me actually start on the right-hand side, analytics. If the use case is really more analytical, right? So you're really starting out with, let's say, something like a query. You're interested in some be that real-time or offline aggregates and so on, then we see more and more people actually being really interested in the table API and analytics. And the characteristics there are, it's just like much easier to write because you're dealing on logical schema, you're dealing with a declarative language, you get automatic optimizations. And you don't actually deal with state and time directly. So state is just something that's implicitly in some of the operators, and triggers and time, you're not really dealing with them because triggers are mainly a way to, to get data out of the program within your SLAs. So, you're really actually interested in specifying SLAs rather than writing triggers. On the other hand, if you're writing applications, these are like very, very physical programs in the sense of, you may have your domain objects, Java classes, Scala classes. You might be actually forced to use them because that's what the libraries with the business logic actually take. You're writing explicit transformation functions. There's no optimization. You have very explicit control. This is how you write it. This is how it's going to get executed. And you have very explicit control over state and time. You can store individual keys and values and in different shapes of state, like maps and lists. And you can register triggers in various ways and have a very, very fine-grained control over what happens, right? But it kind of voids all this optimization that the other side can do. So this is actually how we're trying to rethink the Flink stack a little bit. We're not thinking of the table API anymore as a slightly more easy way of writing a DataStream program, but they're really being fleshed out to kind of cover these different use cases. The analytical use case in the table API in SQL, and the more application use cases in the DataStream API. And of course, because these kind of use cases often are not very clearly defined, there's a lot that's kind of a bit application-y and a bit analytical, or has some aspects of both sides, then of course we still want to make it very easy to mix and match both within the same program. So this is kind of conceptually how are we trying to rethink in the Flink stack, batch processing and stream processing. And Xiaowei is actually going to talk about very concretely what are the first sets of features we're building or we're adding to the system as part of this initiative.
Welcome everyone. Good morning. I'm Xiaowei. I work for Alibaba. I will give you a quick update on SQL notebook and machine learning. Thanks. Yeah, as Stephan just pointed out, SQL is no longer a second-class citizen. It's becoming a first-class citizen in Flink. What it means is when a user writes a table API or SQL program, it no longer gets translated into a data stream or dataset program. Instead, it gets translated into a logical plan directly. Our query optimizer component will look at this logical plan, apply a set of optimization rules, and eventually a physical plan with the lowest cost will be chosen. This physical plan gets translated into a job graph. The operators in this job graph is implemented by our new query execution component. This new architecture is implemented by Flink SQL processor at Alibaba. With this new architecture, we not only re-implemented all the existing functionalities in Flink SQL, but also added all the missing parts. This new SQL processor supports ANSI syntax. It supports all the commonly used data types, including varchar, var binary, or even complex types such as map or struct. It supports all types of joins, inner join, outer join, and full outer join. It supports all subqueries. It supports all windows and all the commonly used group by windows. It also supports advanced analytic functionalities such as grouping set, rollup, and cube. All the queries defined by TBCH and TBCDS benchmark runs in this query processor without any modification. In addition to the functional improvements, we also made a bunch of improvements in the performance in both runtime, query execution, and the query optimizer. Unfortunately, I do not have enough time to go through the details here, but the result we are getting are pretty amazing. For our production streaming jobs, we observed that the performance doubled. Some of them even get a 5x performance boost at production. The performance gain is even more impressive on the batch side. For the 22 queries defined by TPC Edge benchmark, Flink's implementation of SQL processor is about 10 times as fast as Flink's current SQL implementation. And this slide shows you a performance comparison between Flink SQL processor and Spark. For the 99 queries defined by TPC-DS benchmark, this shows you the total execution time for these 99 queries. As you can see, so the lower is the better. As you can see, Flink's advantage is obvious, and it grows when the data size grows. At 10 terabytes, Flink is about 3 times as fast as Spark. And at 30 terabytes, Spark has some problem in completing some of its queries, but Flink had no problem and never hit out memory issues. This new query processor has been put in production in Alibaba since last year. We are running on over 10,000 machines, very high-end physical machines. At any time, there are over 10,000 jobs, Flink SQL jobs running. As Costas just mentioned, in last single day, we processed over 1.7 billion events a second while still maintaining sub-second latency. The largest batch job we have processed over 100 terabytes of data, input data. Table API can be considered as a Scala version of SQL. It shares the same underlying implementation with SQL, so the semantics are exactly the same. But since Scala is a full-fledged programming language, you can use functions or classes such as Scala features to encapsulate your application logic. This makes your application more modular and composable. Sometimes when you write your applications, you may find it's necessary to compose your queries dynamically. Instead of concatenating the strings in SQL, you can use table API to do that in a more elegant and more readable way. We also added support for interactive programming, which allows you to submit some queries, get the query result, look at the query result before deciding which query to submit next. Flink will cache the necessary intermediate result to avoid unnecessary recomputation. We also added a bunch of ease-of-use features in Table API to make it more productive. With this set of additions to Table API, it has become the most powerful, flexible, and productive API for all analytics workload. While we are working on Table API, we also took the opportunity to clean up our architecture a little bit. The idea is that we want to separate the definition of Table API's API layer from its implementation. The API layer will have no dependency with the implementation. With this approach, it becomes possible to have multiple implementations of the same Table API. So the first implementation can be Flink's current SQL implementation, and the second choice could be Flink's new SQL processor. As Costas just mentioned earlier, Alibaba have open sourced Flink as a branch in Flink, and the community has been working at full speed in integrating Flink's SQL processor into Flink. And this is the architecture that we are going to do this. And this Table API refactoring work is defined by Flip 32. We expect it to complete by June. And by July, an initial version of Flink's runner will be integrated into Flink and released as part of Flink 1.9. By October, we expect all the features and performance improvements in Flink will be fully merged into Flink. A lot of you may have chosen Hive as part of your data warehouse solution. So the community is working on Hive integration with Flink. The idea is that once you install Flink in your system, you can use Flink to query and write to your Hive tables. Flink can even make use of your existing Hive UDFs. This saves you the trouble to port your UDF into Flink. With this integration, you can switch between Hive engine and the Flink engine seamlessly. This gives you an easy migration path. There is going to be a talk on the Hive ecosystem integration this afternoon by Stephan and Bowen. You are welcome to join the talks to know more details. To further increase the productivity, we also did notebook integration. In this case, we enhanced Zipling to support Table API. You can also write both batch SQL and streaming SQL in Zipling. Zipling have nice integration with our Flink's web monitor. It can also visualize the static data set generated by the batch SQL program and the dynamic data set generated by the streaming SQL program. Finally, I would like to give you a quick update on the machine learning side. At Alibaba, we have made good progress in machine learning. And we are going to make this a proposal to the community. In our investigation, we enhanced the machine learning pipeline to integrate with the table API. So you can use table as input to machine learning algorithms. In this way, you can use table API to do some pre-processing of your data before you feed it as input to machine learning algorithms. On the algorithm itself, we have made tremendous progress and implemented all the commonly used classical machine learning algorithms. This is just an example list of the algorithms that we have implemented. Our implementation of the algorithms are very scalable and very performant. In this process, we have also accumulated a lot of useful utilities in statistics, linear algebra, etc., that might be useful for anyone who wants to write machine learning algorithm in Flink. There are 2 talks on this topic this afternoon. One is by Xiaowei. He's going to talk about how table API and machine learning works together in Flink. The second is by Xu, who is going to talk about the implementation details on these machine learning algorithms. Next, my friend Robert is going to give you an update on community.
Thank you, Xiaowei. So Xiaowei and Stephan have talked about the impact of our partnership with Alibaba on Flink as a technology. And I would like to use a few minutes to talk about the impact on the community. And I think this is going to be really great for the community because while others in the industry are currently debating about restricting open source, we now have a very big partner that allows us to go all in on open source and really focus on growing the community and also helping it to accommodate for all these changes that are coming in from widening the scope of Flink. So by going into the batch space, by having a unified batch and streaming offering, we'll have more contributors coming in, more integrations with ecosystem partners, and we want to scale the community to accept all those incoming contributions. And I would like to take a quick look at some numbers of the Flink community, and I've picked 2. One is the activity on the development mailing list of Flink, because I think this number indicates the activity of the overall developer community. It shows how much is going on in discussing changes to Flink, in discussing changes in the community, how we want to evolve it. And as you can see here from the numbers, they are steadily going up. We have, in good weeks, we have 230 emails being sent on that list. So the developer community is growing very nicely. The second number I've picked is the number of page views on the Flink website. And you can see that over the past years, we have a very, very nice steady growth in the number of users on the Flink website. And I'm very confident that these numbers will continue to go up. And Apache Flink is already among the top 5 projects within the Apache Software Foundation. And I believe that we will continue growing. And one reason why I believe that we are going to grow in these numbers is that we are currently working on integrating the really big Chinese Flink community into Apache. So at Flink Forward China, we had 1,300 people showing up. And there was a website called flinkchina.org with Chinese Flink documentation. And we are now in the process of working with this group of people in contributing a Chinese version of the Flink website. And this is almost completed already. And we are now in the process of translating the entire Flink documentation to Chinese as well. And I think this is a great opportunity for the big Chinese community to learn the Apache way of doing things and provide resources in their language. We've also launched a support mailing list in Chinese. So I heard that there's a Ding Talk or WeChat group with over 5,000 people that are supporting each other in Chinese. And I think it's very nice of the Flink community to open the doors and provide them a mailing list so that they can learn the Apache way, and also that the rest of the world can see what is going on, how crazy the Flink usage in China is, and also within the ASF to see what is going on there. On the developer side, we've done a lot of work in structuring the community better. So we've recently discussed cleaning up and reorganizing our Jira components to reflect better the changes in Flink. We have a lot more table API components now to reflect that there's a lot going on there. We've implemented a bot that helps reviewing pull requests and that is labeling pull requests according to their labels, so that people working, for example, on table API or machine learning can see which pull requests are open specifically for this area. In a project with over 8,000 pull requests merged, you need some structure and some technology to assist the community. And we're also discussing further improvements to the whole contribution workflow to make sure that people have a really good experience in bringing new code and improvements to Flink. The PMC is working on mentoring and identifying promising contributors in mentoring them to become committers, so that we have more hands in reviewing changes and helping with steering discussions. And finally, we are discussing in the community a Flink community packages website, which might be similar to sparkpackages.org, but we will do this all in the open. So the source code of this portal will be open, and we will host this on Apache infrastructure, on Apache domains, for people to present their work, to present their extensions they've built on top or around Flink, so that other people can comment on it, that they can get visibility and build a community around it. And then we can see whether we want to merge this into Flink or build a community around extensions of Flink. And that's all I want to share about the Flink community. If you have any other proposals, feedback, ideas, reach out to me over the day. I'm really glad to hear what you have to say. Thank you.
Thank you very much, Robert, and everyone. That's basically what we had to share. I hope you're as excited as we are about all these things that are happening. I would like to sum it up in the following way. I think stream processing has made really a very big evolution over the last years, right? I mean, when you think about the early days when it started as, like as a bit of an approximate speed layer in a lambda architecture on MapReduce to what it is actually becoming now. It's becoming really a big overarching paradigm, a way to like build applications that go anywhere between offline batch processing of terabytes of data to real-time transactional applications. And it's for me one of the most interesting things has really been observing how Flink and the Flink community and the people who participate and contribute actually have evolved exactly with this evolution of stream processing, like unlocking these new use cases over the years. And I'm very happy to see that this vision, we've kind of told it over and over again, like streaming, subsumed batch processing, and application. We're actually seeing this all coming over, like seeing it come to, becoming reality over the years. The next step being unlocking this really big part of batch processing, the integration of analytics and machine learning, and very fast batch processing on top of stream processing as part of this technology evolution. And it's not just a bunch of people that are like pushing this in an opinionated way, but it's actually it's nice to see that the community is actually growing with this. It's actually growing with these use cases, and that gets me really excited. And I guess to some good extent that's probably why everyone here is here today of you. And with that I'd like to wrap it up, and thank you everyone.